Good afternoon, everybody. So just a quick reminder that we are doing sensor security. The first project is also out. If you have questions, I see like some people posting question. Let me know if you have any other questions. And the paper presentation is going to start next week. So again, if there's any issue with paper assignments, let me know. Does anybody have any questions? Good. All right. So if you remember last time, we kind of talked about sensor security, and we kind of say that okay, a sensor can be kind of modeled as this, right? A physical domain, an analog domain, and digital domain. And we focused on kind of like this point of this system, which we kind of call transduction attacks. The idea here is that some physical property of the environment changes, and that physical environment, that change in the physical environment is transduced into some electrical signal and propagates all the way through the system, and it will manifest itself as some form of an attack, a problem, right? And we talked about different attack scenarios, attackers' capabilities, the types, in-band, out-of-band, and how do we model it in more formal methods. And we started with some examples. The first one I gave you was an attack to a drone system, specifically attacking gyroscopes in a drone. And if you remember, what we showed was essentially by creating some intentional sound, some vibration will be created. That vibration creates kind of like a positive feedback loop on the gyroscope, and then the gyroscope creates another kind of error to the system, and then eventually the kind of the propellers of the drone malfunction and the system crash, right? So that was one example. The other example that I want to talk about today is attacking to a medical device. Okay, this is called this Ain't Your Dose or sensor spoofing attacks on medical infusion pumps. Quick background on this medical infusion pumps is usually this infusion pumps has some form of kind of like a container that has the medicine. And this medicine has like some form of an IV tube that goes into the body, and they kind of add this medicine. The big thing about this, infusion systems is that it has to be very accurate and has to be very, well controlled. So typically there is some form of infusion pump or some circuitry that kind of controls this. Typically it has also some form of display to send and receive commands. And kind of the idea here is kind of like, the system will monitor this specifically. The pump, the kind of the monitoring system itself is fairly straightforward. It's kind of two kind of IR sensors, visual sensors. That all it does is that one of them kind of constantly sends an array of signal, emit a particular signal, and then a drop will essentially, temporarily will block this kind of emission. And the timing of this kind of blocking is basically telling the system how long each drop is, how big each drop is, and how frequent, what's the kind of the rate of these drops, right? So whether or not the emission is kind of like this IR is being sent from here to here is indication of whether or not there is a drop, right? If there is nothing dropping, then of course these two always see each other's signal all the time. When there are drops, there will be a moment of kind of disconnection between these two signals, right? This is kind of like a very basic method for this. So the attack that is kind of proposed, and it's kind of like this is the basic mechanics of this. These are different drops, as you can see. The emitter always emits. The receiver at this point they will not see anything. So we kind of like you will see a dip into a receiver signal when there is a drop, and then of course this dip would not be like sudden one is kind of a gradual dip, right? Because kind of like signals kind of go away. At some point, there's nothing, and then it's kind of go back up, right? So you see a dip and then comes back. So how does the attacker actually attack the system? What they found was essentially there are a region of this input and output that the sensor kind of this dip is kind of gets saturated, which means that if I kind of do this, I can detect this properly. But if it's kind of like, I do this, right? If I kind of constantly dropping in big drops, then the system at some point saturates, which means that if I add more drops or less drops, there won't be any significant difference into kind of like the dip of the signal. Okay. So in other words, it's kind of like under spoofing, you kind of see something like this. Under normal operation, you will see something like this. And if these two gets very close to each other, then the system cannot really distinguish between the spoofing one and the regular one. Okay. And in other words, this really what it does is that it forced the system to kind of that used to be operating at the kind of linear regime is now operating at the saturation point, so which kind of no longer understand the difference between drops, right? So, and then how do we do that? The attack was basically kind of creating another source of emission here that kind of like, getting close to the emitter and then kind of creating this saturation behavior. Or you could basically try to kind of program the system to kind of operate very close to the saturation point, and during the attack, you actually force the system to saturate. Generally, the idea here is that if your system is operating around this area that's very close to the saturation, then even tiny bit of noise to the system, either external noise or internal noise, could cause the system to malfunction. Okay, so kind of the main takeaway I want you to get from this is make sure that when you're operating a device like this, it has to be enough. It has to be well within this range of linear, so that the small changes wouldn't kind of cause the system to malfunction. Okay, this is yeah, this is kind of like the example of a real attack that they actually have drops, but then they also have like a system that shows that they can cause the system to think that there is a drop or not, or other way around, that there is a drop, but it's kind of concealed that there is no drop. Yeah.
Right? How do you control the amount of thought? I mean, isn't the system with the user, how will the attackers?
So there are two ways that you can attack the system. I believe the paper was talking about like having another source of IR that is close to the device. So think about someone that goes into that room and install something, like use their cell phone to kind of create an IR, these kind of things. That's kind of like the main method. The other one would be a remote user that somehow managed to hack into the system and then cause this different drops. Any other questions? All right. The third one that I kind of talked about this a little bit before is what we call dolphin attacks. These are inaudible voice commands. So this is actually like, gathered from one of your one of your students, some of your students' presentation they did this a few years back. So I just wanted to just acknowledge them. So generally, dolphin attacks is type of attacks that attack voice control system, VCS, right? So VCS is this kind of various different systems that we use. Most of us use like Alexa, Siri, Google, etc. These are all voice control systems that they listen to particular commands that people say, and then do particular activity based on those commands, right? The idea of the attack is, can I send an inaudible signal that it will be captured by this VCS, but of course nobody else will able to understand it, right? So for example, let's say there is an Amazon Alexa in this room, and of course, if somebody says something, we will hear it and we will understand, right? So if the attacker tries to kind of visibly do something, people will notice it. But for example, if one of you kind of play a sound that is in audible range, this particular device might be able to capture it while humans, ears and humans' perception cannot, right? So the idea is that is there such a thing that we can actually kind of like force the system to make a wrong decision? And then you might ask, like, what is kind of the goal of this? There are a whole bunch of things. Like, for example, you can have like a denial of service attacks in the system. So, for example, you can like there are like probably you've seen these videos of like you create this and then all the phones gets like activated at the same time, creating chaos and things like that. There's I think a funny video on YouTube about like something like this happens on Metro. So like, all the phones are like kind of say something like they all hear "Hey Siri" and then you start doing something. You can also force this device to kind of do some action. This action could be like visiting a specific website, or sending some false information, or calling someone, so doing some activity the adversary wants. Or it could be just some form of stealing some information, right? So for example, launching an application to record, and then later on finding some another way to kind of extract this information from the VCS. Generally, there are many ways that the attacker can kind of like, get benefit of the system. To give you kind of like an idea of how VCS works, so VCS usually has kind of like two main components. It has a voice capture circuitry, and then it has a speech recognition circuitry. The voice capture one is more of an analog part of the VCS. Again, similar to kind of a drone, it has some form of a MEMS or other types of a mic. It has the amplifier, the filter, and A to D. So this would be essentially the kind of transduction part of the thing, physical part. This would be the analog part, and this would be the digital part of the system, right? On the speech recognition, usually there's a pre-processing in it that has some words that kind of like some predeterministic words like "Hey Siri," "Okay Google," things like that. That as soon as they see that signatures, they become activated. Okay. If they're not activated, usually they don't really do anything. They just go back to waiting for that kind of like specific voice to come. If they become activated, then they will start doing their process. Another thing that some of these system has is that they can fingerprint the voice. So they have like speaker dependent and speaker independent. For example, the one that I'm showing here is that this pre-processing not only activate the system, but this pre-processing also fingerprinting whether or not this is an authorized user, for example, or not. Okay. If it's an authorized user, then it will activate the speaker. If this is an authorized user, then it will activate the speaker dependent one. If it's not an authorized user, it will activate the speaker independent one. And the reason that these two are different is because not necessarily everybody can do it various different things. So it's more of a security feature. And then of course there is the command part, which depending on which command is coming, it will do proper actions, right? And not necessarily every voice will result in a command. Sometimes your VCS won't understand what you're saying or won't understand the action that you're asking the system to do, but most of the time you will get something like this, right? So how does the attack work? So the attack works basically by creating a command that can activate the system obviously first, and then also can do some real activity, some real actions. Okay. Here I'm showing you the actual kind of the prototype that's been built for this. So they actually use a signal generator. Then they use some speaker, and of course they use some form of a power amplifiers in order to kind of fool the device in a specific format. Okay. And so the signal source essentially goes into like mixed with some signal generator in order to create a signal that's in inaudible range. That's the main thing about the systems. And then another interesting thing that these guys did was they showed that, not only you can have like a tabletop system, you can actually have a handheld or mobile version of this. So it's actually not that difficult to create this inaudible sound just by using your own cell phone. So they actually built this as well, which was kind of interesting. Yeah, I think so how does this actually work? So it works because of nonlinearity of your sensors and receivers. Essentially the way it works is that you can think about a model, a microphone that has a transfer function like this, which S in is the input signal and S out is the output signal. What will happen is that the output signal is a function of the linear combination of input and some more nonlinear higher order effect of the signal. Then what will happen is that usually when we are kind of trying to demodulate the signal, demodulation usually happens with like, changing it to some other frequency. If you want to, for example, low pass filter this, if you want to kind of like, because your microphone gets signal from all different ranges, but if you want to just pick the range that you're interested, which usually is the range that the audible signal is operating, you want to pass the signal into some form of a filter. And this filter, if you know a little bit about, signal processing or analog design, the filter is kind of like multiplying the signal into some form of cosine or sine functions. Okay, so it's kind of moving it from like a higher order to a lower order. Okay, so what will happen if you multiply a cosine to this S out? What will happen is that you will introduce new terms in frequencies. Okay, and that new terms will result in frequencies that are different than those frequencies that you have. So for example, if you created the frequency at FC, it will create frequencies as like FM minus FC and FM plus FC. In other words, if you create some signal at higher order, like at much higher frequency, at inaudible range that you were not supposed to hear it, because you have this nonlinear multiplication effort, you will kind of move that frequency to a lower frequency, which now happens to be in the audible range. That's where the signal will kind of go through the filter. And once it goes through the filter, it's kind of the VCS thinks as if this is a real command and actually do a proper action to this. Okay. So before sending it to the microphone, the signal is at higher frequency. That's why we don't hear it. But once it goes through the system, because of this modulation effect, it goes to a lower frequency. And now that's where the VCS thinks that this is an actual signal. Okay. So this is generally how this works. So the low pass filtering is kind of the culprit here, unfortunately, that caused this things to move. And you need low pass filtering because you want to remove the noise. You don't want to send everything to the system, right? You want to low pass filter it so that you only send a specific range of frequency to the system. But any kind of like an artifact of this is that since this is nonlinear and this is a low pass filter, it will kind of be able to kind of like you can sneak things into your system. That's kind of like what happens. Okay. They actually kind of test this into various different systems. They kind of show it that it works on various different cell phones, and various different, iPads, MacBooks, Windows phones, Google phones, and etc. etc. They also tested different microphones and they saw that it actually works on different types of microphones because almost every microphone has this kind of nonlinear behavior anyway. And then, yeah, the main takeaway of this was that, most of the microphones are indeed vulnerable to these kind of things. Okay? Yeah.
If you use different frequency, the message will be same. The message, however,
So the way that it works is that you create your message, you modulate this. It's the same way that you, for example, think about AM modulation. So you create a message, you modulate this message into some higher frequency, okay? This process is kind of, we create a message, you mix it with another signal, you send it to a higher frequency, okay? This will be your input signal to the microphone, okay? This is not audible because it's at higher frequency, but it has the message embedded in it, okay? And the message itself is a composite message. It has the activation plus the command. So for example, hey, Google, do this, right? So this is the message. When it goes to the microphone, since the microphone has this nonlinear effect plus the filtering, it will try to demodulate the signal, but it will unintentionally will create a component in the audible range. Okay, so it actually passes through the filter and goes through the kind of the speech recognition part of the system, and that's how the attack works. Yeah.
Does the demodulation happen before the filter or after the filter?
The modulation happens before the filter. The demodulation is part of the filter. Okay, so you get the transduction, you create an analog signal, you need to pass this analog signal through the filter. As a result of that, you will get this component. Okay. In other words, if you didn't have the filter, you wouldn't have this attack.
Is it that the filter is nonlinear or the transduction is nonlinear?
The filter is always nonlinear. The transduction has a term that S2 term is kind of going. So if you only had S term and the low pass filter, still nothing would have happened. Yeah, this is just more information about their modulation parameters, the distance. Of course, this doesn't work in all distances. You have to be close so that the speaker can pick up your voice and so on. But yeah, there was like there are actually lots of videos for this. If you're interested, go and take a look. Okay. They also propose some defenses. So for example, they propose that you can enhance the microphone nonlinear range to hires. Another thing that you can do is that added the module before the low pass filter to make sure that it's kind of be able to remove those higher order effects. At the software level, you can also kind of have classifiers in order to detect the existence of such a thing, because they're fundamentally different than regular voice commands. So you can actually kind of detect that there is signatures that seems to be kind of an audible sound, but it's not really. It's kind of the demodulated version of an inaudible sound. And then actually they kind of, I think in the paper, they showed that, this kind of classifier can work. I think they used an SVM for this to show that, a classifier can successfully detect this. Okay. So to kind of summarize of these three attacks, basically kind of the common thing between them is that there are different sensors out there. And as I said, they're like very, very various and variability and diversity of sensors. They have very specific types of operations. Some of them have this nonlinearity, some of them can be saturated, some of them has just resonance frequency and so on, depending on the type. But a sophisticated adversary can actually looking deeply into this operation of the sensors, and they can unfortunately find these vulnerabilities and create signals that's tailored toward that particular sensor. Okay. And then this could lead into various different malicious behavior. It could be lead into denial of service, could cause crashes, could cause, detrimental damages to human body. It could be stealing information and so on and so forth. There's kind of like various different examples that I gave you with these three attacks. And of course, for all of these, the attacker needs different capabilities. For example, the attacker needs to be close to the IR sensor. The attacker needs to be able to modulate the signal in the inaudible range. The attacker needs a powerful speaker to kind of send the signal to a drone and so on and so forth. So you've seen that, there are various different capabilities required. But if you have enough of those, then you can successfully launch an attack. That's why you have to be careful when you're designing a system, like what are those capabilities and whether or not the attacker is able to achieve those capabilities. Okay. There are many more. If you're interested to kind of read about this, first of all, on Monday next week, you're gonna see, I think, 3 more of like examples with more details. So we're gonna actually learn about this. In some of them were kind of similar in terms of themes, some of them were slightly different. I also put 2 references for you in this lecture that you can go and read more about, like more of a comprehensive comparisons of different attacks and defenses for sensors. How do we defend against sensors? Now that we know that there are these possibilities, what do you think are possible detection mechanisms? Any suggestions?
Like secure the physical area of the sensors.
Secure the physical area of the sensor. That's true. But for example, when it comes to something like a drone, it just goes outside, right? So how do you need to kind of like find all the speakers on the ground and kind of like, but yeah, for something like an IR sensor, yeah, lock the door of the hospital room or something should be a good idea, or not letting people, just random people go up. All these hospitals usually check whether you're authorized to go up or not, right? So yeah, this is a possibility. Any other suggestions? Securing the area, one. Any other things? Detection of a potential kind of malicious behavior, like in the example of dolphin attacks. People have shown that, the signal that is kind of translated after the filter is just very different than the regular voice. So you can kind of like extract some features and kind of trying to distinguish. So maybe, for example, same thing could have happened for drones that, the speaker sound is very different. So some form of a detection. Any other suggestion? Randomization, maybe. Yeah. Use a better analog circuits. I will generalize this, right? So use a better kind of analysis or circuitry so that it doesn't introduce new things, right? And then if I want to further generalize this, use better materials such that it has less and less of these kind of physical vulnerabilities. So for example, if I have a system that has much higher resonant frequency, like if I have a gyroscope that has much higher resonant frequency, then it would be very hard for the attacker to create that frequency, right? If it's like or requires much more range in order to successfully attack the system. So these kind of, or like for the IR sensor, if I have much extended period of linear behavior, then it's very hard for the adversary to kind of launch an attack, right? So better designs. So in general, the attacks kind of divided into 2 categories: the detection and prevention. Okay. On the detection is there are various different things that you can do. The first thing that one can do is some sort of like checking whether your sensor is really doing what it's supposed to do. Okay. And this is, for example, is by creating some patterns, some known patterns, and then check whether that pattern is really sensed correctly. This is kind of give you this assurance, this check that whether or not your system as a whole is doing what it's supposed to, right? And you can think about this as sensor to sensor. So there could be like one sensor that you trust and then another sensor that you don't trust. And then you create this first sensor. You use this first sensor to sense the same thing that the other sensor does, and then you compare these 2 results. If they match, means that both of them are doing the same thing. Now we can also expand this to actuator and sensor, or even collaborative. So for example, I create a known signal, I check the sensor to see if they're actually sensing the same thing. Okay, so these are more of to check that whether the sensor is operating normally or not. But in many systems, this is all you need to know about the system. That's, the system as a whole is not being compromised. So that's one thing. Another thing that you do is you have this mechanism to detect out of band signals, right? If you remember, I told you that many of these systems have no idea of what's going on out of their band. Okay, so I need extra circuitry, I need additional sensors to kind of detect those things and remove those things. If I can't do that, then in many of these systems I can protect the system. For example, the inaudible one, if I have a microphone before the other microphone or in parallel with that other microphone that kind of detect that range and kind of notify me that, oh, there is this additional signal in that range, then I can probably kind of detect this or even prevent this. Okay, so additional sensors that could help us to kind of detect out of bands would be very, very helpful. And then similar to this is sensors that can detect the saturation mode of a particular sensor or just abnormal behavior of your sensor. Yeah, like if your sensor is resonating or if your sensor is being saturated, if you can detect those things, again, your system would be secure. And then, as I said, feature detection, that's one thing that someone says that, you're looking at specific characteristics of the system. And if you see that, there is some abnormal behavior of that, then you can say that, okay, there is a potential attacks. And of course, you can use various different machine learning algorithms here. You can use signal processing algorithms here and so on and so forth. Another important one is shielding. If you can shield your system from this noise, then you are safe, right? So the physical checking is kind of some form of shielding, right? But this shielding could be, for example, if your system is going to be attacked by, I don't know, lasers or voices, if you can soundproof it or shield it, that makes the system more secure. And the shielding, similar to the shielding, would be filtering. So you don't necessarily need to shield, but you can also filter before the signal gets in, right? So, and then the filtering could be adaptive, could be fixed. There are various different options here. And of course, the last thing is that some form of randomization. If you can, create somewhat randomly behavior, then the attacker would not be able to predict the behavior of your system. And then if you can capture the random behavior of your signals, then you can also somehow authenticate the behavior of the signal that you're receiving, right? You're expecting your signal to be random. The signal that the adversary creates is not random, so you can actually compare the two. But of course, the problem with randomization is that there's always trade-offs that comes with random. There are extra power or performance or latency that's involved with random. So be careful when we are talking about things like randomization, because you might introduce other extra overheads to the system. And of course, you can always use better design. You have to understand the limitation of the system, use better materials, try to make sure that, things like, saturation never happens, or if it happens, we can detect it. Extending the range of things like resonance and so on and so forth. But better design, unfortunately, comes usually with more costs. So you have to make sure that the cost versus the security trade-off is a meaningful trade-off. And lastly, you want to also use multiple modalities to make a decision. The good thing about multiple modalities is that even if the attacker managed to attack one of them, the other's still working properly. And then if you make a collective decision of these modalities, then your system is secure, right? That doesn't eliminate the security problem completely, but it makes it much, much harder for the attacker to attack the system, right? In other words, defense in depth idea, right? If I have multiple sensors, the attacker needs to attack all of them so that my whole system is compromised, right? And that makes it exponentially more difficult for the adversary to attack the system. All right, so that's it with the sensor attacks. Is there any questions about sensors? Okay, and then you're going to learn more, as I said, next week with the paper presentations as well. And I definitely recommend you to kind of like spend some time reading the papers as well. If you cannot read the whole papers, at least read the abstract or the introduction or just skim through it. It's very helpful to understand this because, as I said, the course is mainly designed to give you the surface level of things. And then in order for you to kind of really go deep into each concept, you have to really spend time yourself and doing the readings. All right, so I'm talking about mostly kind of like transductions, but if you remember, there were a whole bunch of other ways of attacking the systems. The first one was the faults. If you remember, essentially I said that, okay, let's focus on this part. Now I want to focus on this part, the analog or digital faults. So, and again, if you remember, we talked about, changing physical properties of the environment, but now let's actually focus on whether the attacker can kind of create some changes to the analog part of the sensing, and as a result, the system kind of flips. And of course, kind of like, additional to this is kind of digital attacks as well, where something in the digital domain is also flipped and changed. So the faults, in order to give you kind of like, more systematic idea, there are different levels of faults. There's instruction level faults, microarchitectural level faults, circuit level faults, and of course, environment level faults. Instruction level means that I create faults so that instructions are changing. Okay. So for example, you were supposed to add two numbers and now you're subtracting the numbers. Okay. So I'm creating some bit flips in the system such that the activities, the command that is supposed to be there is now different. Okay. Then I can actually go deeper and create macroarchitectural faults. This is, for example, to change one bit flip during the operation of that particular instruction. And then you can even go much further than that and do circuit level faults to create kind of like, delays or not meeting delays and so on and so forth. I'm going to actually give you an example for this. And then finally, you can create kind of more at the high level. You can create changes into the environment that cause faults. So for example, you can heat the device up or shooting lasers or creating emanation, interfaces or laser interfaces and so on and so forth. And then one important things about these is that these are a combination of the analog or digital. So some of them are actually, impacted in the analog world. Some of them are impacted in the digital. Okay. So I'm going to talk about, a few of this. I'm going to talk about physical faults. I'm going to talk about what we call DVFS faults. I'm not going to talk about Rowhammer, but I'm going to talk a little bit about, oops. Thank God. Sorry about that. I don't know what happened, but it's just stopped working for a moment. Was it updated? Oh, wow. Anyway, so I'm going to also talk about jamming and contamination. In other words, spoofing as another form of faults. All right, so what are fault attacks? In general, fault attacks is that I want to create some malfunction to achieve various different goals. Okay, this goal could be, again, integrity, availability, or confidentiality. So I can create some information leakage, I can create some integrity issues, or could create some form of a denial of service. One important assumption about hardware that you have to keep in mind is that I kind of reiterate this, and I said this before as well, that general problem with fault is that when it comes to hardware, we are always assuming that the hardware is properly running my software without any issue. Okay, so there is always this implicit assumption about hardware that it always correct. We always assume that there is correct execution of the software on hardware, and the problem with faults is that this basically breaks this assumption that that we create this intentional issues, errors that propagate through the system, that now no longer the software that's supposed to be secure is actually running correctly on my hardware. Okay. This is a nice picture that's kind of like give you a full end-to-end overview of the system. It can start from all the way from the physical level. You can create some faults. You can create this faults to the circuit level. You can create this faults at the hardware or microarchitecture level, and then eventually we'll show their manifestation at the software level to create some form of attacks. Okay, so similar to transaction, there's various different modalities for faults. You can kind of create glitches for the clock. You can do overclocking. You can change the voltage or frequency of the system. You can create electromagnetic emanations. You can create lasers or pulse and all those things. And again, the examples that I'm going to give you 2 examples, and you will see that, there's various ways that we can create faults in the system. Important things about faults is that fault intensity is an important thing. Similar to the transaction attacks, the amount of the changes that the attacker can cause to the system will create, lots of impact to the system. But generally, fault signals are very, very tiny, right? So you want to be able as an attacker to kind of create a strong, impact to the system in order to have a meaningful impact in terms of attacks. And for the faults, the timing is also very important because, for example, assume that you want to change 1 bit flip, like you're going to cause 1 bit flip, right? That 1 bit flip should be exactly at the time that you wanted it to be, right? So it's not like, a drone attack that, whenever you kind of like, run the speaker, the system will crash. It's the right time, right place that if you create that fault, it will propagate all the way through the system and cause a crash. Okay. So timing is important and intensity is very important. Another thing that's very important with faults is that how much do you know about the internals of your system? In other words, whether this is a white box attacks or whether this is a black box attacks. That do I know that like these are all kind of different activities that's happening in my system, or is it more of like, oh, I just know that the system is supposed to do this. I don't know exactly how it works. Okay. And finally, you can have remote attacks and you can physical attacks, physical fault attacks versus remote attack. The physical ones is that the attacker should be present there. The signal is actually part of the physical environment. The remote one is that you change, for example, something internally into the system and that will cause a fault. Okay. So to give you one example, this is actually a very famous one. And that people have found that, if I can kind of manage to flip 1 bit, and if that 1 bit that I flip is at the very, very last stage of, for example, AES, what I will be able to do is that now I have control over 1 bit of my kind of like intermediate stage of my ciphertext. Okay, so consider, for example, that without the fault, what I had was I had this V, this kind of like, let's say, for example, I have a 10-round AES, that the very, very final round, the output of the final round, what I would do is that, for example, I just go through the S box, the kind of mixing, and then XORing it with a key. So I would have initially it would have V and K, and it would have got C. So now what I could do is that if I just manage to flip 1 bit, okay, then I can do what I can do is kind of like now I have V prime and C prime. I know exactly the rest of this because I know exactly what happens here. The only thing that I don't know is this key K, but now with comparing these two, the C and C prime and V prime, and all the internal activities here, I can actually extract 1 bit of K. That's that 1 bit that I flipped, I can extract that 1 bit for K. Okay. And now what I can do is that I can repeat this process for all the bits, right? So I can, let's say if this is 256 bits, if I create this fault 256 times, each time for one of the bits, then I can essentially extract the entire key, right? So this is kind of like based on this assumptions that, but the tricky thing is that I need to kind of issue this fault at the right time. That's when the 9th round is finished. If I do it at the 8th round, then there is no point. If I do it at the 7th round, there's just no point. I need it to at the very, very last part, and I should be able to just flip this with 1 bit. Okay. So there are lots of ifs. You have a question?
Yeah.
Yeah.
Let's just assume that we don't have like a none, so some more other term when the implementation of the ciphertext won't be the same if you don't change it.
Good question. So this is assuming that there is no none. So here is that everything is controlled by the adversary, so they can actually run the same nuns, right? So for example, let's say I have access to a device, okay? So I can send inputs to it, okay? What I would do is that I send the same message and same nonce. I want to figure out what is the key inside, okay? So it's not supposed to be a secure mechanism here. I just said I send the exact same input twice, and I see the same output each time. But now what I would change between these 2 runs is that one time I flip one of the bits using the fault. That's really what I want to do. Say it again.
You know the message, the input, like you can decode.
Because I want to find the key, because remember in attacks, we said that even if I know a limited set of M and C's, I still cannot find K, right? So in crypto, we said that this is what we call like CPA and CCA secure. That if I know even that the limited set of M and C's, the key still won't be detected, because you want to find the key to be able to decrypt any messages. Yes, you have access to a limited set of M and C's. For those that don't care, but I want to find the key so that I be able to decrypt other messages. No, the key won't change, right? So the key is your symmetric key here. You change your nonce every time with the message, but you won't change your key, right? The key will never change. Does that make sense? Any other questions? So again, going back to this is like very, very controlled attack. It's not something that's always is happening, but the key idea here is that it's possible that if you have this potential control and doing single bit flips at the right time, you can essentially extract the key. Okay, that's really the point here. But let me give you a few more realistic examples. So before that, I want you to show you this, that there is this thing called manifestation and propagation, okay? So remember that, for example, in this particular case, we flip this bit, okay? But the manifestation, but this error should propagate all the way through the ciphertext. I should see the ciphertext is changing, and then I should be able to kind of extract this key from the system, right? So the idea here is, your system is going through the processes, it creates the fault, the fault is kind of manifested through the system, you observe it, and then that's where you actually see the impact, okay? So the manifestation and propagation of your fault is actually what is happening here. And then usually this goes through the hardware all the way to the software. So for example, in this particular case, if I can issue the fault is kind of at the circuit level. But what you will see is that changing the ciphertext at the software level, right? So it goes all the way through the software. And then another thing that you have to keep in mind is that there is also regular faults in your system, okay? So faults can happen all the time, things changing, there are transient noises, there's particles, there's various different things that cause faults. So faults is not something that we never see, and we only see it in adversarial samples. The difference between a transient or a regular fault versus an attacker's fault is that the intensity of the attacker's fault is significantly larger. Okay, and the timing of it and the behavior of it is very, very well planned. Okay, so that's the major difference between regular fault and fault attacks. That's why we have what we call fault tolerant systems, right? The systems that can occasionally see some changes to the system and still manage to kind of like, you know, operate normally. But fault attacks is kind of different in the sense that the timing, the frequency, the rates, they're all very, very different. Okay. Let's have a quick break. I'm going to come back and talk about this particular examples of faults. Yeah. All right. So I'm going to talk about the two, one or two. At least this one is a quite interesting one. It's called clock screw. And the next few slides is actually kind of borrowed from the original presentation. So the idea of this is, can I change the operation of the system, the chip, such that by changing this, I will create some intentional faults, okay? The paper also talks about how do I use these faults to do something meaningful. I'm not going to talk much about the second aspect of it because that requires some other knowledge, but I'm going to talk specifically about how they actually create those faults in their attacks, okay? To understand how they create these faults is they are using this thing called dynamic voltage and frequency scaling. They play with that and they show that that actually can cause faults. The interesting about this type of faults that they created is this is completely software control. Okay, so kind of like, you know, the figure showing here is that using software you can actually modulate and change this DVFS manager. That will create different operation ranges, changing the voltage and changing the frequency. That change in voltage and frequency cause faults, and then that faults will be manifested into some secret knowledge. So in this particular case, they managed to find the keys, cryptography keys of an encryption mechanism. Okay. So the main cool thing about this paper was that all of these things doesn't even require physical access. So you don't need to go and change the voltage or change the frequency manually. You can change all of these things, you know, remotely. Okay. So how does it work? So in order to understand how does this work is you have to understand what is DVFS, dynamic voltage and frequency scaling. Dynamic voltage frequency scaling is kind of like, you can think about this as a hardware software unit. So kind of DVFS sits between the software and hardware. On the software side, you have one thing called power governor, and you have kind of like some drivers. And then what they do is that based on some algorithms, based on their set of policies, they make decisions about what should be the voltage regulator and frequency regulator. In other words, what should be the operating range of this device? For example, you probably heard about, you know, frequency of a CPU, whether it's like 4 gigahertz, 3 gigahertz, things like that. That's not like one single number. It's kind of changing depending on the workflow. I'm going to describe that very soon. So that number is decided by this software, this what we call a governor. Those of you who play with Linux a little bit, you probably have seen this, that you can actually change this governor. And then there is like a depending on like which device, the actual device you're using. Are you using an Intel board, like Intel CPU, which type of Intel CPU or an AMD CPU? There's a specific driver for it. In other words, long story short, there is software that decide what is the operating voltage and frequency. That will translate into some circuits, and that circuit is basically kind of applying this. Okay. The question is, why do we even want to change voltage and frequency? The reason is that I want to manage my power. Those of you who are a little bit familiar with VLSI design, you will see that, you know, the dynamic power of your system is kind of a function of three things: the capacitance of your circuit, the voltage that it operates, and the frequency that it switches. Okay. So it's kind of like dynamic power is equal to CV squared times F. So the lower the F is, the lower the V is, and the lower the C is, the lower your power is. Of course, in many of the mobile systems and battery power systems, you want to minimize the power as much as possible, right? So you want to minimize F and V as much as you can, okay? And C is more of like a circuit thing, like you really cannot change it most of the time. But F and V I can change, okay? But then the question becomes, why don't I just like use the minimum possible V and minimum possible F and done with it? Why should I want to have this dynamic? The answer to that is the faster the voltage is and the frequency is, the lower the delay is, okay? So the delay is kind of the inverse function of voltage and frequency. So the higher the voltage, the faster your system can work. The higher the frequency, the faster you can switch. In other words, your system is a faster computer, okay? So you kind of like, in order to minimize the delay, in order to build faster computers, you want higher frequency, you want higher voltage. On the other hand, for lower power, you want lower voltage and lower frequency, okay? So these two kind of disagreements, right? There's on one hand, you want faster systems, on one hand, you want lower power systems. So what you would do, in order to balance between power and performance, you use DVFS, which is kind of saying that, okay, I'm going to keep the voltage and frequency at minimum and only increase it when I need to. So I kind of do it on demand, okay? So for example, if your system is idling, okay, I'm not going to use a very high voltage or very high frequency. Your system going to switch at very, very low rate, okay? But then when you need it, then I'm going to, you know, jack up the voltage and frequency, okay? It's similar things happen with your cell phone. Like when you kind of push it on, then that's when you're going to start seeing the voltage is jumping up and voltage frequency is jumping up. That's what we call dynamic voltage and frequency. That's why we usually have this to kind of decide where this should operate, okay? Interesting about voltage and frequency is that they typically, there are pairs for them, okay? So they're usually called operation pointing pairs. So for example, what I'm showing here is for Nexus 6. This is kind of like what at the time of this paper they were looking at it. So as you can see, it's kind of like, you know, the x-axis using voltage, the y-axis using frequency, and it's kind of like this, that frequency kind of stays constant for some time. The voltage the voltage stays constant, the frequency kind of goes up. Then at some point you kind of increase them both, but it's not like, you know, voltage and frequency gets any arbitrary values. They're usually values that kind of pairs between them. So these are kind of recommended operating range, okay? So usually we have like somewhere between like 10 to 20 different operating range. These are kind of predeterministic tables within the source voltage governors. Once you kind of turn on your system and start using it, it's kind of moved toward this direction. This direction, like kind of like going up, this corner is the fastest corner, but it's the less power efficient corner. This corner is like the slowest corner, but the most power efficient. So we kind of go with this one, okay? That's the idea of operating point of DVFS, okay? And then the interesting thing is that, of course, you can have different points. So technically, you can have all these blue points that I'm showing you here. And there is a thing called instability, which means that if I kind of go beyond a voltage or go beyond the frequency without improving the other, I'm going to reach to an instability point. The reason that I'm going to have an instability, I'm going to show you in the next slide. But generally, you have to kind of follow specific pairs. If you don't, your system will start doing random things. And of course, the attack is exactly kind of like exploiting this, that we're going to have points here that creates the system unstable, and as a result, create faults. And these faults can propagate and then can cause harm to the system. That's kind of the basic idea of this paper. And then the interesting thing is that, of course, there are different instability points for different devices. So for example, for device A, this is kind of like the envelope. For device B, it's a little bit lower. So the attacker kind of also needs to know where for each specific device, where are these points. So some profiling is required in order to launch this attack. So why we have this instability? The reason for this is kind of like go back to like very deep circuit level things. Those of you, how many of you knows what is a flip-flop? Okay. No, do you know how it operates? Like, do you know how many of you know what is the setup time and hold time? Okay, some of you. So to give you an idea, flip-flop, as you know, is this units that kind of work with the clock and store some values, right? So they are kind of like, storage units in our circuits. That if you have an input, if the clock comes, they usually edge triggered, which means that by the positive or negative edge of the clock, they sample whatever input they have to the outputs, okay? So like the clock comes at this point, this input is stored here, okay? So they have some memory, okay? So they remember things. And then not necessarily all the components in our system needs to be flip-flop. We usually have what we call, combinational logic in between, that they don't have any memory. They just, whatever the inputs comes, they do some operations and they have an output. These are different gates that we have: AND gates, XORs, OR gates, etc., right? And then typically you can think about any system that you have as a combination of what we call this sequential logics like flip-flop, and this combinational logics that they don't have any memory. And we typically kind of like sandwich this combinational logic between two sequential logics so that you can kind of think about this as kind of like task, right? So data comes, it's stored here, it goes through this, and then comes here, stores here in the next cycle, and goes to the next one. So you kind of like we create this kind of pipeline-ish behavior of things goes into between two flip-flops, do some activity, goes to the next, between the next two flip-flops, do some activity, and move forward. That's usually how we design circuits. Okay. So what's important about this is that when I operate this system faster, when I change the frequency and voltage, two things will happen, right? The first thing that will happen is when I change the frequency, the clocks are kind of gets closer and closer to each other. So the time between this data that propagates from here to here becomes much, much smaller, right? Because what used to be, for example, 1 nanosecond is now half a nanosecond or like 1/10 of a nanosecond, right? So if I clock this system faster, this process has to happen much faster, okay? That's one thing. The second thing is that if the voltage goes up or goes down, the delay of the circuit also changes, okay? If the voltage goes up, the delay goes down, which means that this process can be done faster. If the voltage goes down, this delay goes up, which means that this process is slow, okay? So as a result, what will happen is that obviously, since this part is kind of constant and the delay of this is known, you want to kind of switch your clock. You want to set your frequency such that there is enough time for the data to be updated here to propagate all the way to here, okay? If I switch faster than this propagation delay, then I'm going to lose values, right? I'm not going to get the correct outcome that I'm expecting. Right? So that's where things gonna get kind of like iffy, right? That if I switch very fast, but that doesn't really increase the voltage. That's why if you increase the voltage or increase the frequency, you have to increase the voltage as well. So that if you clock faster, you have to decrease the delay. Okay, so that's kind of like the basics of this. Otherwise, what will happen is that you're going to get what we call timing violation. In other words, you're expecting this value, for example, to be 0, but what you're getting is just a random value. It could be 0, it could be 1. Okay, that's why we call this unstable, because sometimes it might be the correct value we're expecting. Sometimes it's just there's not enough time for this value to propagate all the way here. So it just gets some random value. It could be 0, it could be 1. Okay? Questions? So this is how the fault would occur. That you kind of, so this was just for 1 bit, but then you can actually kind of expand it to multiple bits. So consider, for example, you have a large number and you have all these flip-flops and all these circuits for each bit. You're kind of expecting, for example, this value, but some of the bits are not really fast enough, so they kind of like flip between 0 and 1. So as a result, for example, you get something like this. So some of the bits supposed to be 1 are now 0. Some of the bits that's supposed to be 0 is now 1. Okay, that's kind of the idea of how this faults will occur, that either I increase the frequency without increasing the voltage, or I increasing the voltage without increasing the frequency, either of those. Okay, So how do we actually use this in order to break the system? As I said, this is more of the details in the paper. What they showed was I will create this false, and then I kind of like cause this RSA decryption mechanism to kind of like decrypt this incorrectly. And if we think that this is kind of like a right file to use, but in other words, it's not. Don't worry about this part because we need to understand what is a trust zone and what's the difference between normal and trust zone. We're going to come back to this part actually later in the class when we are actually talking about trusted execution environments and so on. If you're interested, you can definitely go and read the paper. But the whole point of this is that if I can change the operation of the system, I can actually induce this false. I can flip bits. And then what do I do with those flip bits? That's a separate questions that this paper answer it. There are many other papers who answer, kind of like do it separate. Okay? Questions? Cool. So what are the possible defenses for a system like this? So first of all, what you can do is that you can limit the operating, pairs in your system. So you cannot let the system to kind of pick arbitrary points, or if it does, you can kind of like limit it or detect it. Another thing that you can do is that you can have like redundancy, you can have regulators, you can have different microarchitectural kind of solutions for this. Eventually, I mean, generally, there's kind of like you can change the circuit such that it doesn't have issues like this, or you can like kind of make sure that the system is not operating in this unsafe behavior. Okay. At the software level, of course, what you can do is that you can eliminate the effect of faults, which means that I can create some randomization. I can run the code multiple times. I can do these tricks in order that even if the fault exists and propagates through the hardware, doesn't really create any meaningful activity at the software level. So that's kind of like the idea of how do we protect the system. Okay. Questions here? All right. So that's kind of like story with faults. There are a whole bunch of others that I think there might be one of the papers readings next week that talks about faults as well. But if you're interested, there are more relevant things that I'm going to post on Campus Wire about this. Okay. So kind of like the last thing I want to talk about sensor attacks is jamming and contamination. So another form of sensor attacks is that kind of not sending wrong information to the sensor, but preventing the sensor from sensing. Okay. And this is what we usually call jamming, and in other words, in some cases, contamination. Okay. So for example, assume that you have a radio, right? You're waiting for an important message to be received, or you want to communicate with the rest of your group. Okay. If the attacker kind of disable your sensor, in other words, doesn't allow you to sense a new RF signal, then this is kind of like a denial service attacks in some sense, right? And this is very important, especially in like high assurance systems, such as, let's say, you have like a military systems in wars, you have I don't know, an airplane, things that needs constant communication with some base station or some other groups. And if you can kind of like eliminate the possibility of this communication, then you're essentially kind of like creating damage and harm to the system. So again, the goal here is not creating wrong inputs, it's just eliminating the inputs to the system. Okay. And contamination is another way of a special case of this, that you don't necessarily create errors at the moment. You're not interested to cause like a fault or attacks at the moment, but you want to kind of feed the system with wrong information such that in future you can use this. So for example, think about this, is that if I build any sort of like a learning model on the system, I can feed the system with wrong information. So the model that will be learned based on this data is a wrong model. In future, I'm going to use this wrong model to do some various different things. So for example, think about authentication as an example, that somebody if wants to penetrate into a system, what they can do is that first, force the system to think that this is kind of like a valid and legitimate users. In future, they can then now have a kind of a backdoor to the system. Okay. When we talk a little bit more about machine learning, you will learn about these things that we usually call them poisonings. But for sensors, you can actually contaminate your sensors this way. Okay. How do we actually do the jamming? Once we start talking about RF security in 2 weeks, you will see that, for example, you will see an example of jamming. But I wanted to mention it here to kind of know that this is kind of technically part of sensor security, because it's a different way of sensor security, but it's still a sensor security problem. Okay. So what are the general countermeasures for sensing? I kind of described this over the different examples that I talked about. But for faults, you want to improve your robustness. In other words, you want to be less and less sensitive to any sort of faults. You want to use software controlled method in order to kind of make sure that even if there is faults, you can properly detect it, right? And then you want to have detection mechanisms for detecting faults. So for example, you see that, oh, my voltage or frequency pairs are not in the right group, or things like, oh, I see like abnormal behavior on my system that it shouldn't be there. And finally, you can isolate your system such that faults cannot go through your system, right? Again, if, for example, changing the temperature will cause faults to your system, maybe it's a good idea that you put it somewhere that the attacker cannot change the temperature. If DVFS is another thing that you're worried about, maybe isolate the remote users from changing your frequency operation points, right? So any sort of isolations from a potential adversary are going to give you security. Okay. So yeah, these are things that you can take a look to learn more. So the first paper is kind of give you a survey of various different electrical fault level attacks. The second one is specifically for cryptography. How do we actually introduce faults in cryptography? And the third one is actually talking about more of RF and 5G systems, and how different ways of creating contamination, jamming, or sensor attacks could cause different problems to the RF systems. Definitely take a look. It's not part of like your reading list, but if you're interested, take a look. Okay. So to summarize this kind of like, this module, computer systems are generally vulnerable to this phenomena, and that when they are actually kind of interacting with the physical outside world, they are not secure, because the attacker can change the physical domain. They can cause problems during the operation of the system, and unfortunately, there's not easy ways to kind of prevent this. So this is kind of like one of the main reasons that our systems are not secure. Okay. All right, so that's for this part. Let's have like 2 minutes break until I load another one. I'm gonna briefly talk. Okay. So the next module that we want to talk about is what we call side channels. I'm gonna just briefly go over it to kind of give you an overview, and then we're gonna talk more next week. So far what we have learned is we have sensor attack scenarios. We talked about transduction, we talked about denial of service, we talked about integrity, and we talked about digital. But there is a big what if that I want to discuss in this module, and that is that we so far said, what if, like, the impact of the physical world on our digital systems, right? So for example, the attacker can change the environment one way or another, and that will cause different issues, different faults, different attacks to our system. But there's also the kind of the flip version of this, that what is the impact of our computers to the physical world? Okay, that our computer can also change things in the physical world, and that could be potentially interesting. Why would we care that like our system could cause difference and cause changes to the environment? The reason for this is this could potentially be an area where there is information leakage. essentially this is what we call side channels. In other words, the idea here is that think about this very, very simple problem that let's say your computer heats up when it's doing something, okay? So the heating will create kind of like some heat that kind of propagates through the air. So someone outside that can measure this physical phenomena that your computer has impact to the environment, they can measure this using some form of a sensor, okay? So some heat sensor, temperature sensor, that's close enough to your computer that can measure how much, heat your computer is generating, okay? So by measuring the heat, I can essentially kind of correlate this information to the activity within your computer. Like very, very simple thing, I can tell whether your computer is on or off, okay? So why would that matter? For example, let's say I can do this behind a wall. I can essentially, by just measuring the temperature of your computer, tell whether you are there or not, right? Your physical presence can be detected by just measuring a temperature, right? So for example, your neighbor can measure the temperature and see whether your computer was on or off. Another more interesting thing would be, for example, let's say different applications that you're running has different amount of processing power. Some of them need more processing, some of them need less. As a result, some of them will generate more heat, some of them will generate less heat, right? So again, if I can measure the temperature of your computer outside without even looking at your computer or knowing which application you're running, I can tell the difference between applications. Let's say, for example, I have a good profile of 100 different applications that you could potentially run. What I could do is that now I can kind of measure the things that I'm seeing over right now versus the kind of the database of different profiles that I have. Now I can tell whether you are really, for example, doing something like doing application A or doing application B. Like for example, whether you're really I don't see your computers, but if I have a temperature, can I see whether you're watching a YouTube video or whether you're listening to my lecture, right? So these are kind of like the things that the attacker can do. And that's why it's very, very important for us to know that what sort of information leakage this potential behavior has, right? And this temperature is just one example. There are many, many more that I'm going to talk about in this module next week. Another problem that we want to know about side channels is what we call covert communication. The idea of covert communication is that I can use this kind of behavior that I can kind of impact the physical world as a method to send information out, okay? This is usually what we call a covert communication as opposed to regular communication or overt communication, which in regular communication, you want to send a message to the outside world. You actually design your system, you do everything intentionally, okay? But now think about data exfiltration ideas, right? So where you, for example, go to a specific building or a specific area that you're not supposed to, for example, take out your phone, or you're not supposed to kind of record anything, okay? If you manage to find a way to communicate your data to the outside world without using any of your regular communication words, then you can kind of exfiltrate or steal this information and send this information out, okay? So that's very important, because if I want to make sure that my system is secure and nobody can really kind of take anything outside of the system, I need to make sure that I'm robust and I'm secure against covert channels as well. Okay, so these two things are the main two reasons that we care a lot about side channels. So yeah, as I said, this is kind of like the impact of computing world to the physical world is what we call side channels. And these are completely unintentional. So something to remember is side channels is not something that we create or we want to be there. They're just there because of physical phenomena. So for example, your computer heats up is not something that you can eliminate or you can control or something that you would want. It's just something that is there because of the physics of electrons moving. The moving of electrons create heat. and that heat has to dissipate, right? So that's why we have side channels. Interesting about side channels is the exact opposite of sensing. If you think about sensing as sensing something from the physical world into the computer, side channels is kind of like sending some signal from the inside to the outside world, right? And then, as I said, how and why they exist is because of different physical phenomena, right? Each one is there because there is some rule of physics there that caused this. Two examples of side channels are like the famous ones is power, change and fluctuation in power, electromagnetics. Because of the switching activity, there will be some electromagnetic signals. Temperature, as I said, sound or acoustic, time. These are all various different examples of side channels. Interesting thing about side channels is that there's generally two categories of side channels. There's what we call digital or microarchitectural side channels, and there's what we call analog or physical side channels. Digital and microarchitectural is because of sharing a particular component in your system. So this could be your cache, this could be your memory, this could be your TLB, this could be many other things. In this class, we don't talk about physical side channels, digital side channels. This is the case for another course that we're actually going to talk about later on next quarter. But the focus of this class is like this lecture is analog or physical side channels. Analog physical side channels, as the name suggests, is analog signals that are created in the system. And as I said, examples are electromagnetic, power, temperature, sounds, and so on and so forth. The big difference between physical and digital is physical requires some physical proximity. It requires some physical sensors. So usually you need some tools to be able to measure this. And you need to be kind of close to the device in order to be able to pick up the signal. The interesting thing about physical is that isolation won't help you with physical, which means that if you kind of completely disconnect this computer from the outside world, you don't have any Wi-Fi connection, Bluetooth connection, no input, no output, you're still going to have physical side channels because, again, the temperature is not something that you can eliminate in the system. Versus digital side channels, you can eliminate by just isolation. If you not let this computer to connect to any sort of like network, you are safe in terms of digital side channels, okay? But if your computer is quote unquote air gap, which means that there is no connection with the outside world, you're still vulnerable to physical side channels. That's physical side channels is such an important problem. And as I said, we're not going to talk about digital side channels in this class. All right. One last thing before I let you go. What is the goal of a physical side channel? The goal of the physical side channel attacks is usually extracting something sensitive. Physical side channel attacks are not availability or integrity issues. You don't change something on the system. You just extract the information from the system, okay? So it's just purely confidentiality issue. It's not integrity or availability issue. You want to extract something from the system. What would you extract from the system? Of course, the first and most important thing is some form of secret. And those secrets are usually cryptography keys, okay? So most of the side channel attacks and literature in side channel attacks is revolving around some form of breaking decryption, okay? But this could be any other sensitive data. So for example, if you have passwords, credit card numbers, I don't know, social security numbers, if you have any sort of IP or software that is important to you, any document that is important to you, technically all of these can be extracted using side channels, okay? And then as I said, another goal of side channels is communication. So you want to use this unconventional channels in order to exfiltrate some data. So you want to, for example, change the heat, and by changing the heat, you want to send a message. Think about like a Morse code, that if I increase the heat, it means that I'm sending 1. If I don't change the heat, I'm sending 0, right? So like I basically kind of modulate the temperature rise or fall to send a particular message to my neighbor, right? And this is what we call a covert channel that we're actually going to discuss in the next lecture. All right, I think this is where we should stop here. We're gonna let you guys go a little bit earlier. But next time we're gonna do the paper presentation first, and I'm gonna start talking about sections. Okay? Any final questions? All right, see you next week.